So welcome to my presentation on GPU Workcraft, the future of GPU programming. I'm Matthäus from AMD, and at GDC I would have been presenting this with Sean, but here it's without Sean. So let's get started. GPU Workcraft is one of those moments in GPU history where the GPU programmability really makes a step function improvement. So if you remember back in the day when programmable shaders became a thing, that was like one of those very large improvements in programmability. And there wasn't really that many of those in the history of computer graphics. So today we had another one of these Workcrafts, and I hope by the end of the talk you will agree with me that this is really the new dawn of a new time in GPU programming. And if not, you can obviously ask questions. So the motivation here for Workcrafts is fairly easy. If you have been talking to game developers over the last couple of years, most of them will have asked this question here or expressed this wish. If only I could launch work on the GPU. And if you talk to some of the more experienced ones, they will tell you they can actually launch work on the GPU using ExecuteIndirect. But they will also tell you it's an awful programming model. So while they're doing it, it's fairly reluctant to do, they're fairly reluctant to do so. And if you talk to hardware designers, driver developers, and authors of GPU debugging tools, they will tell you that ExecuteIndirect is indeed an awful programming model. And we should get something better in place because that's really not the long-term future here. And before I get talking about the solution in the Workcrafts, I just want to make sure that everyone is on the same page as to what the problems actually are. So I will walk through a very simple example of ExecuteIndirect and where it fails today and why. So this is a very typical use case you have today. So you have a producer shader which generates data, which can be consumed by one of 4 different consumers. So those consumers are simply different shaders. And you want to somehow produce into like each of those buckets and then execute the work and consume it. So the way you do it today is you just allocate 4 buffers, each of them the worst case size in case all the work goes into one bucket. And the producer runs, increments an atomic along the way, and then just writes the data into those buffers. So in this case, it has written data for the consumer 1 and 3, and consumer 2 and 4 have not gotten anything. So this is fairly straightforward, but it has a bunch of problems. So first of all, you obviously need a barrier. So you need to finish producing all the work you have in flight before you can start consuming it. This is particularly bad if the producer is very fast or is not very uniform in terms of execution time. And then you have empty launches. So this way, draw and distro here or dispatch here, they don't do anything. So you just walk through the CP, it executes a no op, and then you continue. And if you imagine you have 10,000 consumers, this obviously becomes fairly quickly a significant problem. And then you're also wasting memory and potentially a lot of memory. So in this case, it's not as bad as it looks like here actually, because it's only 4 buckets. But imagine you have 500 buckets or 5,000 buckets, and you want to bin, for example, every single pixel. Then you need something like 8 megabytes times 5,000 buckets of memory. So that clearly becomes prohibitive very quickly. And there are many existing problems which are really opportunities for Workcraft. So today, for example, recursive algorithms like scene traversal and whatnot, they tend to be implemented using something like persistent threads. And then you can traverse the scene and call yourself recursively and process meshlets in the leaf nodes. So that's one thing you can do. Another one is adaptive algorithms. So you want to identify how many threads to launch for each tile. For example, you have a physics simulation. You want to figure out, is this tile 100 objects, 1,000 objects, should I launch this kernel or that kernel? And then you can do it with ExecuteIndirect today, but it becomes fairly expensive fairly quickly. And then one use case, which is increasingly common, is very long execution chains of indirect calls. So in the first one, you're running a screen space ray tracer. So it produces a result for, let's say, half the pixels. And then some of those rays will be running very long, so you have to wait for them to terminate before you can start the next dispatch, which actually fills in the rays where the screen space ray tracing failed. Now, that ray tracer may also not fill all pixels because there's like no hit result or something. You will also have to wait for that one to finish, and now you have started fewer rays, and some of them might be running for a long time because the variance in runtime of rays is very, very high. And then all of them terminate your barrier again, and you start a local cube map upload for the remaining pixels. That might be only a couple hundred. And then you have to clean up with a global fallback for whatever pixel remains, and that might be only like one. And the problem here is obviously you have to start the world, stop the world after the screen space ray tracing, you have to stop again after normal ray tracing, stop again after local cube maps, and you can't overlap them. What you can do is you can do something like this. You can start parallel chains, so you can try to tile the image and then have independent execution chains, but there is really no way to express on the GPU today how you synchronize those things. So we have seen ISVs trying to open like the 100 compute queues and try to express this with 100 barriers on separate compute queues, but that doesn't really work either. So this is just something which is incredibly difficult to express on the GPU today, but it's a up and coming problem really, because you have those things where you have 100 objects, each object has a bunch of meshlets, you want to unpack the meshlet and then do something with it, and then another pass and so on, and you just want to overlap like each individual pass here, and you don't want to put them all into one Uber shader because of occupancy issues and whatnot. Another example, which most people should be familiar with, is function calls, which really is the ray tracing problem, right? So you have a material selection shader, and then it can go to one of 1,000 different materials. So obviously with 1,000 boxes, this becomes very busy. So I'm only doing 6 here, but imagine there are 1,000 different shaders you want to call, and then you have 1,000 buffers where each pixel could be in one of those shaders, and then it becomes totally prohibitive. And obviously some of those shaders may be very similar and whatnot, and there's like no way to express it and merge them automatically and so on. So with the stage set, let's move on to Workcrafts, the next generation of GPU programmability. And imagine, what if the GPU could actually decide when and what to launch? So not do the ExecuteIndirect where everything is pre-recorded in the command buffer. What if the GPU could allocate and free the memory, so you don't have to provide all the memory up front? What if you could use all of this today? And that's actually true. You can. I mean, it has been released at GDC, actually a week before GDC already. So you can give it a try if you want to. Okay, so GPU Workcraft, what is it? It's a data flow model first and foremost. So it doesn't talk about execution. It really talks about the data which is flowing through the system. And the data in this case is called work items. So it's like work moving from a node to a node. And the work items, you can think of them as like a struct, like a couple of bytes basically. Then work items get queued up at the individual nodes, and once enough work is pending, then the GPU launches a dispatch. So there's no ordering, nothing in here. It's like all left up to the GPU. But the way you can think about it is like nodes with queues, and then data is moving between them. And just to make this a bit more clear, so you have those nodes. Each node is connected with edges to other nodes. Each node has a virtual queue. Important, this is virtual, right? It doesn't have to be like an actual queue somewhere in memory. And the nodes launch as soon as enough work is waiting for them. And enough means it depends on the GPU, it depends on the driver, it depends on your graph. And in particular, what the runtime can do is it can merge and fuse nodes, it can reorder outputs, it can introduce sorting and whatnot. So all of those things means that if you think about this from the logical perspective, the scheduler launches this dispatch here to consume the data which is waiting for this node. But in reality, it might be just fused together with the producer, for example, and then they just launch together, or there is a reordering happening before it, and so on and so forth. Speaking of the launch, so you have some control over the launches, and you can select how they launch. So there are 3 different launch modes, and work items can basically do one of those 3 things. So they can trigger dispatch, broadcast. So there's one work item coming, and it gets broadcast to one or more fixed size thread groups. So you specify this in the work item or upfront, and you're saying like, if this one work item appears, I want to launch 1,000 threads. And then it just launches those 1,000 threads, and the work item is available to everyone for reading. That's called broadcasting, and the work item is broadcast to everyone. There's another launch mode called aggregating. So you have a virtual queue which is filled up to some degree, and then it launches a fixed size thread group for up to those n items. So you specify how many items you can consume. Like I can consume up to 64 items, and I want to launch 64 threads every time. And the runtime will try to queue up to 64 items. It might be only 5, it might be 64, and then it launches. And it's your task to figure out like how many items there are pending. And then one of your user specified thread group is processing the data. So one important thing here is to keep in mind that like if your queue is very empty and you're still getting all the threads you asked for, right? So you might be asking for 256 items, but you're only getting 16 items. And then you better do something with your 256 threads on them. And the final one is if you only care about work items and you just want to launch one thread per item, it's called thread launch mode, surprisingly. And it does an unspecified grouping of work to threads. But you can't tell anyways because every thread is independent. You just get one work item. And from the thread's point of view, it processes only its own work item. And there's a completely unspecified execution here. So this is, for example, the mode if you just want to do something like ray tracing and you only care about launching one material or something like this. There's one more case here we need to talk about, which is node arrays. So far, the way I've been explaining it, if you have many different nodes, you would have to send an entry to each of them potentially. And if you have many materials, that is fairly cumbersome actually in the API to express. And there's a much better way to do this, which is called node arrays. And the key point of a node array is it has a uniform input type. So it means it's safe to send it to any node in a node array because all of them have to consume the same input. So previously, if you had 10,000 independent nodes, all of them can have a different input type. And if you stream in another node, it's just, you don't know if it's going to be compatible or not. For a node array, you know it's compatible. So that's the easy thing here. And it's also very easy to select which node in the node array you're targeting. It can actually vary per lane, for example. So if you have a distress ray shader, it can attach the node ID inside the node array to the payload, and then it just gets routed to the right node. So this is a fairly lightweight way to do it. It's also more efficient than trying to just assemble a graph with many nodes. And it's also type safe, as just mentioned. So. And then you also have recursion, but it's only self-recursion which is allowed. So there's currently no loops across nodes. This is for forward progress guarantees. It is possible to eventually extend this, but for now, this is limited to self-recursion. The total depth and expansion is also limited, again, for the same forward progress reasons. Right now, the maximum depth of a graph is 32. Recursion actually counts towards this, right? So if you self-recurse, then it increases the depth of the node. And the maximum expansion is 1 to 32,000. And if you do the math, it's 32 kilobytes times 32 depth level. So in the worst case, like one input byte can expand up to one output megabyte, and you need to do this reservation upfront. So that's the reason why this is limited, because otherwise you couldn't guarantee forward progress. Like imagine if you want to guarantee 1,000 threads here in this worst case, you already need 1,000 megabytes of memory just to make them launch in the first place. And 1,000 threads is pretty bad occupancy. If you're getting limited by the total depth, where you have very deep trees you might have to traverse or something like this, the usual best solution here is to just fuse multiple traversal levels into one traversal step. So instead of just going like one traversal level and then spawning a new work item, you do like 2 traversal levels at the same time. And that's really the only limit which has required some work so far. Like everything else seems to be fairly generous. In terms of syntax, it's plain old HLSL really. So you take a function and you annotate it, and then it turns this function into a node. So you can think of annotating the function to be like a message passing mechanism really. So that you can see this is a fairly small amount of extra text you need to write here. The important part here, this is written in such a way that you can reuse the code between compute shaders and Workcrafts. So it's fairly easy to have the same shader being used for both. You still need to compile them twice, but at least it doesn't mean that you have to rewrite everything. So in particular, if you have existing code using ExecuteIndirect, converting it to Workcrafts is fairly simple and straightforward. Calling other nodes, that's where the message passing really shines through. So the way it looks like is you allocate a record and then you fill it out and then you send it off. That's really all that's happening here. So you can see this get thread node output records, that's the allocation. Then you fill out the payload, so you have to write the payload before you send it. And then you call output complete and the message is gone. So that's like an async remote procedure call, really. At that point, it never returns. So from this point on, the workload is just in the system and it will be processed at some point. Okay. And before I go into specific examples of how to use this, the first question is usually, can I beat the black box? Because obviously here is a very large black box attached. And the answer is yes, sometimes you can beat it with heroic programming. If you are a grand programming wizard, you can do persistent threads and then somehow make it work. I like to call them persistent threads because they really don't scale very well. So if you have the optimal number of threads for one GPU, it's not the optimal number for a future GPU. And you don't even know if a future GPU or another GPU cares about the occupancy you're reaching or the number of threads is even optimal for it in any case. Like a new driver version can come, it can increase the number of registers used, and then your carefully selected optimal number of threads is wrong. You can also use custom memory management. I mean, we have been saying like the easiest one is to just increment a buffer and then increment atomic and fill a buffer, because that's what ExecuteIndirect really likes to. If you're writing your own GPU memory manager, I mean, probably you can do a pretty good job there. Again, you're probably looking at like a couple of many years of development time. Especially if you're on console, you can pull like low-level synchronization tricks, which may or may not guarantee forward progress. But the point here is really not that you can't beat the system at all. The point is that Workcraft makes all of this accessible, easier to compose, and gives the runtime optimization freedom. And easier compose is the part that I can't stress enough here. If you have the world's best persistent thread implementation with the best custom memory manager, and you have another world's best persistent thread implementation for another part of your runtime, and now you're trying to combine them, well, then good luck, right? And in case of work graphs, it really just works like this, right? You take the one graph, you take the other graph, you throw them all together into one big one, and it all works. And same for like a memory management. If you have one memory manager and now you have a different memory manager and you try to compose all of this, it just becomes super hard. And down the line, this gives optimization freedom and also enables new features, as we'll see later in this talk. So the current model is really hard to extend. And we'll see here in a minute why this one is more amendable to extensions. All right, so let's go into practical applications, workgraphs in the wild. So one example we have here is compute rasterizer. And what you can see here is a visualization of the triangle size. So basically blue means fairly large triangles and red is fairly small triangles. And if you've ever written a compute rasterizer, that is actually the main problem with compute rasterizers. They need to deal with varying triangle sizes. On today's GPUs, that means you ideally sort by size, because what you want is like one wave process 32 triangles which are 1 pixel in size, and another wave process 32 triangles which are 4 pixels in size. What you don't want is one wave processing a 1 pixel size triangle, a 4 pixel size triangle, and a 32 pixel size triangle, because that means you are paying the runtime of the worst case triangle. So the 32 pixel triangle will basically keep everyone else hostage. So the way you can do is you can do one bucket per size, and then which can hold potentially all triangles you care about. If that's like 10 million triangles and you have 15 buckets, that's already a fair amount of overhead. You also need to do a barrier between producer consumer, and you need to be very careful what you're doing there, because if you are transforming the triangle to estimate the screen space size and you want to store all of this information away, that's quite a bit of data. If you want to recalculate it afterwards, then well, you have to recalculate it, but you only have to store the triangle ID. So that's already a big trade-off in terms of memory versus computation. And with workgraphs, all of those problems really go away, right? So you don't have to be worried about the temporary memory, because you can calculate the screen space bounding box and then send it to the right rasterizer. It is also fairly easy from the implementation side, because these are all the same rasterizers. And as a bonus, you can also handle clipping, which I didn't mention before as a problem even, but imagine if your triangles can get clipped, you don't even know how many triangles there will be in the end, right? So even if it's perfectly sized for your input, for certain viewports, you might get like twice the number of triangles and then it just breaks down. And that can't happen here. It's like the memory usage is bounded. And we have done an implementation of this, which you can grab from GPU Open. And just to give you an idea of like how much memory savings we're talking about here, it's 2 orders of magnitude down, at the same time improving performance a bit. Okay, so another one is procedural content. So these days, game worlds are becoming very, very large. So if you're playing a modern open world game, they tend to be like in 16 square kilometers or something in size. And in that case, you just can't fill up the whole world manually. So there are things where you can do this procedurally. For example, in Blender, there's something called geometry nodes, and Houdini is heavily node-based. And then you can create a node graph, which procedurally fills up the world with content. So those complex decision trees, they are very hard to execute using ExecuteIndirect. Like you have many branches and connections in those graphs, and it's like, what's the worst case IV count in this graph below here, where you have a bridge builder which can place IV, you have a castle builder which can place houses and walls and an IV on them, and that is a town builder as well. So you can start trying to move those things to the GPU by unrolling, linearizing the whole thing, doing a topological sort, allocating output buffers, checking which buffers can overlap. And a couple of years later, you'll be probably done, but it could be still unbounded intermediate memory you're using, even if the final output is actually bounded, which may still make it impossible to actually run this code. So that's pretty bad. And that's why we looked at this one. And here's our procedural enrichment demo. So what we have been doing in this procedural enrichment demo is we haven't tried to like replace things really, but just make them look nicer by adding work graphs and then running additional code which cleans up, which makes the scene more interesting. And we actually have a live demo prepared for this one. So that's the scene. This is without procedural enrichment. So you can already see all the grasses coming from there, but there are actually quite a few more details we look at. And the first thing I want to go to is to the meadow here. So, and that's over here. So we're replacing this grass procedurally, but this grass is not just placed procedurally where roads should be, removed the road should be, and then placed everywhere else. This grass is also doing multiple decisions here. So where it's sunny, it's placing additional flowers and occasionally bees flying around those flowers. And where it's dark areas, it's actually placing mushrooms. And this is all based on a classified and execute part, basically. So it goes for every single tile, it classifies which one it is, and then randomly places those additional details. So we look at this in 1 second. Then we also have a bridge here, which is overgrown with ivy. And this is a part where we have a recursive creation. So if I go over here, you can see how this starts. And then you can see the ivy growing, and it also splits up so that you can see this. It's not just recursive, but it's also amplifying. And that happens multiple times across it here. And there's actually another piece of ivy here. And actually all the big ivy patches you can see are doing the same thing here. So we'll also look in a second into how this one works. And then we have a fairly large example of procedural content, which is this market. So the first interesting part to look at here is those roads here. They're also procedurally generated, and they actually interact with the market. So we specify a polygon where we want to place the market in. This is one is recursively subdivided by a work graph. So this is the first recursion level. Then we fill in the roads, and you can see how they connect with the remaining roads. Then we place market stalls. We place guirlands between them, and then we fill it up with additional props here. So, and this is how we get this market. And you can also see that this is a fairly deep recursion possible. So we can scale up this market a bit in size, and you can see it still works, and it's now many, many levels of recursion running here. Okay, and there's actually one more thing to show here, which is all of what you're seeing here. So this is the work graph procedurally generated content. But this is a Workcraft which is extended using the draw call extension. And this is actually the whole Workcraft. So everything you see but the skybox is going through the same Workcraft. So all the draw calls in the scene are going through it, including all of the procedural generation. So this is literally one draw call, one Workcraft dispatch to create and render the whole scene. All right, that's the demo. So let's talk about individual effects in detail. The bridge. So growing Ivy just forward is fairly simple. So while you want to continue to grow, you just create new items. This is a very simple implementation, right? So you can do this in any GPU programming language today. But the problem arises when you try to do this here. So now we are growing and we are splitting the paths. So we have a fork here, which continues to grow forward in this fork. So basically we are spawning a new branch of Ivy here. And if you try to do it today, well, you have to use some kind of persistent threads and then somehow fork by writing it to a work queue or a stack and then like work until that stack is empty or something like this. And with Workcraft, this is super easy. You just literally emit the next record if there's a fork in the road, and then everything just works. And you don't have to worry about memory. You don't have to worry about forward progress. It just happens to work. For the market, I mean, this is this multi-stage graph. So we look into this in a second. So this is actually the whole graph here. So we have this market placement, which is the recursive subdivision of this input polygon, which is then sent into two different paths here. So one is creating the market stalls, one is creating the actual paths, like the roads between them. And then we have those additional props which connect between the market stalls, and we have the props which are being created to fill up the remaining space. And they are also called recursively because those props can fill up the space in multiple steps. So we place bigger props first and then smaller props afterwards. So first step is the market. So we just define the polygon in which we want the market to grow. And then we recursively subdivide this polygon. So this is this step here. And that creates the areas where the market stalls goes in and where the paths are. Then we create those paths, and you can see it connects here with the remaining paths. Then we place the market stalls. Then we have those guirlands here to connect them. So this is another node in the graph, which is just run after the market stalls have been placed. Note there is no synchronization currently in Workcraft. So this is one of those things where you need to figure out a way how to make sure that you don't have conflicting results where like two paths cross or something. So we resolve those conflicts manually, basically, and that's how we get this to be stable. And then we place those props recursively, and this is how you get this scene here. Okay, and we move on to the meadow. So this is the last part here, and this is where I'm happy to talk about this preview feature, draw nodes or mesh nodes. Basically, what this allows you to do is not just do the scene traversal and the procedural enrichment in the Workcraft, but also do the actual draw calls. So again, this is a preview feature. This is not part of the first release, but it's coming somewhere down the line. And this is not just draw calls, it's also draw calls with PSO switching. So that's a long dream from many ISVs to switch PSOs, and now you're getting this one here. So the way this works is it feeds into a mesh shader pipeline. So you can think of this as an amplification shader on steroids. It's the whole Workcraft basically turns into an amplification shader, and then your mesh shaders are running in the leaf nodes. And the runtime tries to make sure your PSO switching isn't too expensive. So it will obviously try to buffer up draw calls. It will optimize the state changes. And from your side, the more similar the states are, the better. So the cheaper state changes, just swapping out shaders, basically. And with that in place, the grass generation is actually fairly simple. So we have a classification shader, which looks at every single patch. And then if it's sunny, it produces a grass patch and then draws it. If there's no sun, it produces mushrooms additionally on top of it. If there are flowers, so this is when it's sunny and there's some random element to it, you just get those additional flowers. And in the case of flowers, you can also get some bees. And if none of this is happening, but it's still sunny, you can get some butterflies potentially. And there was no execute indirect used here at all. So this is all going through a single work graph, and then that work graph is producing mesh calls at the leaf nodes. So some stats for the demo. We have 37 nodes with 9 draw nodes, and we're producing 6,600 draws per frame. You might think that's fairly small, but that's because we're using mesh shaders and can obviously coalesce things together before we kick off a very large mesh shader. So in total, it's 30 million triangles we're looking at here. So that's a solid number of triangles per draw call. The whole transient memory this graph uses is 196 megabytes. So that's fairly low if you consider there's 200,000 work items flying around the whole system. And what I haven't been telling you so far in the demo is everything you saw there was running every time in every frame. So all the procedure generation was actually running every single frame. You could cache it and be smarter about it and regenerating all the grass and all the markets and everything every single frame. But it just happens it runs so fast that we didn't even bother to optimize this. Some super early numbers from like what the performance expectations can be. So in this case, we also have an ExecuteIndirect path, which does all the drawing. And if you run this one, it's 50% slower than the Workcraft implementation you just saw. So that's a already pretty significant uplift, especially considering how early in this in the stage, again, how early on stage we are at the moment. But that's like one data point here. Speaking of performance, there's a bunch of things you should not try with the first implementation. So obviously, the smaller the launches, the worse the performance are. So if you have 1 million nodes in your graph, and each of them is only getting one work item, Workcraft won't save you either. So you should try to not be too fine-grained. Ideally, just think of like every single node is getting a few thousand work items, or at least launching a few thousand threads which do something useful. Then you should try to keep your payload small, ideally a couple of bytes, right? So like send a matrix around, send an index around, something like this. If you need very large amounts of memory, you should probably write them into a UAV somewhere as well. Don't try to synchronize yet. There is a bit of wording in the spec how you can synchronize. It's very easy to shoot yourself in the foot, and we have better ideas in the making. And you probably don't need it at first either. So when you're trying to port like existing algorithms over, there's probably no need to synchronize them in the Workcraft itself yet. So like leave this for later. And then if you have coalescing nodes, you should always check like how full they are if you can, right? If you have a coalescing node which is expecting a lot of items, you should be doing some instrumentation yourself to figure out like what's happening there. You can also use tools. So the AMD Radeon GPU profiler is shipping with support for Workcraft, so you can see like all the individual sub-dispatchers happening and whatnot. So that should give you an idea like what occupancy you're reaching with your Workcraft and whatnot. So far I've been talking about D3D. So what about Vulkan? So Workcrafts are also coming to Vulkan. There's an AMD X extension. So it's AMD only and experimental. But as usual, we want to match the D3D with an EXT or KHI extension. And we plan to release updates to the AMD extension in tandem with new features in D3D. So you can expect that Vulkan will be on parity for the foreseeable future. And with that, I come to my last slide. So Workcrafts are GPU managed producer consumer networks with expansion and reduction. So you can amplify with recursion. They give you GPU managed memory, so you can never run out of memory. Even if your intermediate data is potentially unbounded, it will just start applying back pressure and then churn through it. And it gives you guaranteed forward progress. So there's no way to deadlock or hang this by construction. So if you don't do unsafe synchronization tricks, your Workcraft will always terminate when it can actually launch. And the best of all of this is available now. And with that, I want to thank a bunch of people. And then you can read the disclaimer. And that's it.